In this next module, I'm going to delve a little bit deeper into permutations and combinations, the counting methods. So I'm going to review two types of permutations and combinations. These are the basic counting methods. So we're going to go into more detail than in the earlier module. So we'll talk about permutations. Permutations are where you care about order. We're going to talk about permutations both with and without replacement, and we'll also talk in more detail about combinations. That's where order doesn't matter. So first of all, starting with permutations. A permutation is an ordered arrangement of objects. So again, we're going to consider order when we're talking about permutations. Permutations can be either with replacement or without replacement. So with replacement means that once an event occurs, it can occur again. So if you roll a die or flip a coin, it's equally likely that you're going to get a 6 on the next roll or a heads on the next toss of the coin. It doesn't matter what happened before. You have replacement. Things can repeat. Without replacement, the event can't repeat. So for example, if you draw the ace of spades out of your deck of cards, it's gone, and so it cannot repeat. So we're going to start with permutations with replacement. So with replacement, again, are things like coins, dice, DNA, as we're going to see. These are called what we call memory lists. That is, let's say you've flipped a coin 5 times in a row and you've gotten heads 5 times in a row. Most people intuitively think, well, I've already gotten 5 heads, now somehow the probability that I'm going to get a heads on the next coin flip is going to be lower. But that in fact is not true. Coin flips are memory lists. So it doesn't matter if you've gotten 5 heads in a row, the probability that you're going to get a heads on the next coin flip is still 50%. So you have an equally likely chance of getting heads on the next toss. So again, that's with replacement. And DNA also, if you think about A, T, C, and G, the letters in DNA, you can have an A and then another A and another A. So one of the possible codons is AAA. Just because you've used up one of the nucleotides doesn't mean it can't repeat. So you can have repeating there. So let's start with a simple permutation with replacement problem. So what's the probability of getting 2 heads in a row when tossing a coin? So there's a number of ways we can solve this, but we're going to do the counting method way. So that means, again, we're going to count up all the possible outcomes in the denominator and put in the numerator all the outcomes that fulfill getting 2 heads in a row. And the easiest thing to do here is actually to kind of draw out a tree. So on the first toss of the coin, I can either get a heads or a tails. No matter what happens on the first toss of the coin, on the second toss, I can still either get a heads or a tails, and all of those outcomes are equally likely. Heads and tails are equally likely. So there's 4 branches here, and there's 4 possible outcomes. So if we look at all the branches, here's my 4 possible outcomes. I can get a heads followed by a heads, I can get a heads followed by a tails, I can get a tails followed by a heads, or I can get a tails tails. Notice we're considering order. Heads tails is considered different than tails heads. There are 4 possible outcomes here. The only one of those that's getting 2 heads in a row is this top branch. So 1 out of 4 is my probability. 1 out of 4 branches fulfills the probability. So my probability is 1/4. Here's another example. What's the probability of getting 3 heads in a row? Okay, so to solve this one, we're going to have to draw out a bigger tree. I find it useful to draw out these trees when you're learning about permutations and combinations because you start to get a sense of things. Eventually you won't need to draw out the trees, but it's helpful to sort of draw out the trees to see the pattern. So in the first toss of the coin, you can get a heads or a tails. The second toss of the coin, again, you can get a heads or a tails. The third toss of the coin, again, you can get a heads or a tails. So we can enumerate all the possible outcomes when we flip a coin 3 times. We could get heads, 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 tails, all the way down to tails, tails, tails. There's 8 possible outcomes that we can get here. Now notice that a pattern is starting to emerge, right? So we have 2 possible outcomes with every flip of the coin. We have a 2 here, and then we have 2 again, and then we have 2 again. So notice what we're doing is just multiplying the number of possible outcomes again and again. Since everything gets to repeat, we just are multiplying the same number over and over again. Well, we can also shorten this by just raising to a power. Another way to say this is 2 cubed. I have 2 possible outcomes, and I'm tossing the coin 3 times, so there's going to be 8 total possible outcomes. So I got 8 branches in my tree. How many of those are 3 heads in a row? Well, only that top one, heads, heads, heads. So my probability of getting 3 heads in a row is 1 out of 8. Here's another example. When you roll a pair of dice, or 1 die twice, what's the probability of rolling 2 6s? So if I roll a die of 2 dice or 1 die twice, what's the probability of rolling 2 6s? And what's the probability of rolling a 5 and a 6? So for dice problems, the same thing. So in the denominator now, we're going to count up how many possible outcomes are there. Well, there are 6 possibilities, 6 possible outcomes when you roll a dice, and we're going to roll 2 dice. So the denominator here is going to be 1. It's going to be 36, 6 squared. And there's only one way to get 2 6s, so the probability will be 1 out of 36. So notice the pattern that's starting to emerge. Everything is involving powers. What's the probability of rolling a 5 and a 6 when you roll 2 dice? Well, the denominator is going to be the same, still 36. Now we have to count out all the ways that you can get a 5 and a 6. So there's actually 2 ways you can get a 5 and a 6. You can get, remember, we're considering order here, so you can either get 5 followed by 6, or you get 6 followed by 5. Those would be separate branches if you were to draw out the branches here. So the probability of getting a 5 and a 6 is 2 out of 36. So you can see that a pattern has emerged here. When we have permutations with replacement, so order matters, and with replacement, we're going to be using powers. The base, what I'm representing as n here, is the number of possible outcomes per event. So for dice, there's 6 different possible outcomes. For coin flip, there's 2. And then you're going to raise to the power, which is the number of times you're repeating that event, that coin flip or that toss of the dice. So we're going to be using powers, and then we end up with n raised to the r power here. So notice when you have replacement, these are actually the easiest ones for the counting methods because we're just dealing with powers. Everything repeats, it's nice and symmetric. Let's just do one little practice problem here. If you want to challenge yourself, pause the video, see if you can do this on your own, and then restart the video and I'll lead you through it. So the problem here is, how many different codons of DNA are possible given that there are 4 nucleotides? So the 4 nucleotides are A, G, C, and T. There are 4 possible nucleotides. And in genetics, a codon, which is the word, the basis of forming amino acids, each codon has 3 nucleotides in it. So how many different possible 3-letter words are possible from the 4 letters A, G, C, and T? So the answer, of course, is going to be 4 raised to the 3rd. There are 4 possible letters, and we get to put 3 of them into spots in the codon. And order matters, right? Because, for example, you know, AGT might be a different codon that might code for a different amino acid than, say, GAT. So there are 4 raised to the 3rd power, or 64 different possible codons. And again, this is considering order, and we're allowing replacement because you can have 2 A's, you can have 3 A's within the same codon. All right, now moving to permutations without replacement. These are things like cards. So again, once you draw the card out, unless you reshuffle them, that card is gone. A lot of the examples that get used in basic statistics courses with permutations are seating arrangements. So we're going to use some seating arrangements. So for example, you are moderating a debate of candidates for governor. How many different ways can you seat the panelists in a row? And let's just give them easy names. A, B, C, D, and E are our 5 panelists. I want to know how many different ways can you seat those 5 panelists in a row. This is without replacement because once somebody sits down in one chair, they're gone. You can't have the Ariana be repeated twice, right? It's a person, so she cannot repeat. So this is without replacement. So how do I solve this one? So again, to get a grip on, to get a feel for how to solve these basic counting problems, a good idea is just to draw up the tree which enumerates all the possibilities. So that's what I'm going to do here. So you can also do just a trial and error method as well. So this one, it's going to take you a while, but you could try to just write out all the permutations. If you're just beginning to learn probability, when I was learning probability, I actually did often try to just write out all the possible permutations. It just gave me a sense of confidence to see that how many I wrote out matched what was coming out of some formula. So we could systematically write out all the permutations. You could write out A, B, C, D, E. What's another possibility? A, B, C, E, D, A, B, D, C, E. You could keep writing them out. Now, obviously, this is going to quickly become difficult. There's a lot of possibilities here. It quickly becomes a pain. You know, you really don't want to have to write them all out. But again, when I was first learning probability, I really did sit down oftentimes and try to write a lot of things out just to get a sense of it and to convince myself that what was coming out of the tree or the formula actually matched what I could enumerate by hand. So easier than systematically writing out every permutation is just to figure out the pattern by using a probability tree. So again, I really like these trees. I think they're very useful for understanding permutations and combinations. So think about each branch of the tree, each node here, represents a different seat. So when you've got the first seat, you can sit anybody in the first seat. There's 5 possible candidates, A through E, and you can sit any one of them in the first seat, right? But let's say, for example, that you sit C in the first seat. Now C is sitting down, so he or she is no longer able to sit in any of the other seats. So if you go down the branch, if you sit down C in the first seat, then the possibilities for the second seat are reduced down to 4, A, B, D, or E. And same as if you sit E in the first seat, then the possibilities are reduced down to A, B, C, or D, again 4 for the second seat. So you go from having 5 possibilities down to 4. And then for the third seat, it's going to be down to 3. And for the fourth seat, it's going to be down to 2. And the fifth seat is going to be down to 1. So you start with 5. You multiply that by 4, you multiply that by 3, etc. So each branch gets pruned. So it's, for permutations, you're dealing not with powers, but with factorials. It's going to be, there's going to be 5 times 4 times 3 times 2 times 1, or 5 factorial ways to arrange those 5 people in 5 different seats. So without replacement, when we're doing permutations, we're going to be dealing with factorials. What, however, would happen if I changed the problem a little and I said you had to arrange 5 people in only 3 chairs? In other words, you got to kick 2 out of the debate. And again, we're doing this randomly. What are all the possible ways that you can sit 5 people in only 3 chairs? Well, to solve that, we can again write out the tree. So in the first chair, there are 5 possible people that we can put in the first chair. In the second chair, there are 4 possibilities. In the third chair, there are 3 possibilities. And then whoever doesn't make those first 3 seats is out. So we don't have to keep going. So the number of different ways we can arrange 5 people in 3 chairs is just 5 times 4 times 3. So it's like a factorial, but notice we're truncating it before we get to the end of the factorial. So it's just slightly different. Now, it would be perfectly fine for a small problem like this to just write down 5 times 4 times 3 and calculate that out. But imagine I had given you a bigger problem, like 20 people arranged in 15 chairs. Then you would have to write out 20 times 19 times 18 times 17. It's going to be this really, really, really long product. So I'm going to show you a shorthand involving factorials, a shorthand way to write what I just wrote here, 5 times 4 times 3. So another way to write 5 times 4 times 3 is to recognize that that's the same as 5 factorial divided by 2 factorial. Because we want 5 times 4 times 3. If I divide 5 factorial by 2 factorial is 2 times 1. The bottom, the end of 5 factorial is 2 times 1. So those will cancel and give me back 5 times 4 times 3. So what I've written here, 5 times 4 times 3, is equivalent to 5 factorial divided by 2 factorial. I'm going to go one more step with this because I'm going to eventually want to generalize this. So rather than writing 5 factorial divided by 2 factorial, because in the original question I asked about 5 people in 3 chairs, I'd like to stick with those original numbers so that we can eventually come up with a general formula. So I could write this as 5 factorial divided by 5 minus 3 factorial. Notice that's just the same as 2 factorial. So I'm going here and trying to come up with a general formula for this type of permutation. So if I want to arrange 5 people in 3 chairs, it's 5 factorial divided by 5 minus 3 factorial. If I wanted to arrange 10 people in 7 chairs, we could use the same logic to show that it was 10 factorial divided by 10 minus 7 factorial. And you can see that this actually also works, this little general formula works if we're talking about 5 people in 5 chairs. Remember when we solved that one, we just said it was 5 factorial, there was no denominator. But the denominator's there, it's just hidden, because if you would apply this general formula, you would say 5 factorial divided by 5 minus 5 factorial, which is just 0 factorial. Well, 0 factorial is just 1. So this simplifies down to 5 factorial, but it fits into this general formula. We can also use this with the card examples that we talked about in the last module. So how many 2-card hands can I draw from a deck when order matters? We actually solved this in an earlier module. So again, we can write out the tree. There, on the first draw, I have 52 possibilities. On the second draw, I have 51 possibilities. So I showed you before that that's just 52 times 51. Well, 52 times 51, what is that really? That's the same as 52 factorial divided by 52 minus 2 factorial. Now, it looks harder to write out the 52 factorial divided by the 52 minus 2 factorial, right? It looks harder to write that than to just write 52 minus 51. But you can see that this is going to be a more compact way to write a lot of examples that might fit into this. So again, we have 52 cards. We want to pick any two of them. It's going to be 52 factorial. In order matters 52 minus 2 divided by 52 minus 2 factorial. So there's a general formula emerging here. We didn't really need the formula for this simple example, but imagine I give you a more complicated one. So, for example, what if I say, how many 10 card hands can I draw from a deck when order matters? Well, I could write out 52 times 51 times 50, da 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 da. That's a really long thing to write out. Or I could simplify it. So that's the same as 52 divided by 42 factorial, which is the same as 52 factorial divided by 52 minus 10 factorial. So again, this kind of general formula is emerging. If I've got 52 cards and I want to make and 10 of them, draw out 10 of them where order counts, it's 52 factorial divided by 52 minus 10 factorial. So we can see that there's a general formula that's emerged here. If you have a permutation, order matters, and you do not have replacement, instead of using powers, you're going to use factorials. And the general formula is that if you've got n people or cards that you're drawing from, and you want to arrange them in, say, R chairs or R draws of the cards, then the formula is n factorial divided by n minus r factorial. So that is a little formula that you can use to help you in solving when you have permutations without replacement. One little practice problem, again, if you want to pause the video and try to solve this on your own and then restart the video, it's a really good exercise to test yourself. I'll walk you through it as well. So a wine taster claims that she can distinguish 4 different wines. So if you cover up the wine bottles with some paper, sometimes it's fun to do at parties, and you have her taste the 4 different wines, can she actually identify which wine is which? Let's say she really has no wine tasting ability. What's the probability that she can do this? She can get all 4 wines correct just purely by chance. So with 4 unlabeled glasses, 4 covered bottles. This is without replacement because she is not going to be allowed to guess the same wine variety for each of the glasses. So you imagine she's got 4 little names of the wines on stickers, and she's got to stick those stickers on the 4 different glasses. So she's not allowed to repeat her guesses. All right, so to solve this one, we're going to calculate the numerator and the denominator here. There's actually only one way she can get it right, so the numerator is easy, it's just 1. But how many total number of guesses could she make if she's just guessing randomly? Well, there are 4 glasses. She's got to identify 4 wines with the 4 glasses, so it's a 4 factorial problem. For glass 1, she has 4 choices. Once she's said glass 1 is this particular Merlot, then she's down to 3 choices. And then for glass 3, she's down to 2, and for glass 4, that's by default the last one. So this is a 4 factorial problem. She's got 4 wine names that she's got to arrange on these 4 glasses. And so that's a 4 factorial, so that's our denominator. So the probability that she can do it merely by guessing would be 1 divided by 4 factorial, or about 4%. So the last thing we're going to do in the counting methods is combinations. Combinations are where order doesn't matter, where you're not going to consider order. And these will always be without replacement. It's very tricky if you somehow wanted to have order doesn't matter with replacement. So we're just going to talk about order doesn't matter, and we're going to assume all of the order doesn't matter ones will be without replacement. I mentioned in an earlier module the choosing function. It's written as n big C R, or n over r in the parentheses, and we read that as n choose r. Those are 2 different ways to write the same function. It's a function, and I'm now going to kind of walk you through the derivation of this function. So let's start with an example. How many 2-card hands can I draw from a deck when order does not matter? So ace of spades followed by 10 of clubs is the same as 10 of clubs followed by ace of spades. And usually when we play cards, in fact, we really don't care about the order in which things were drawn. So it's more natural for us to think of cards with combinations. So how many different 2-card hands can I draw? We actually calculated this in an earlier module. Remember, if you consider order, it's 52 possibilities times 51 possibilities, but if you want to not consider order, since there's a double of everything, everything is repeated once, you can just divide by 2 to divide out the order. Now I'm going to write the 52 times 51 in our new formula for permutations without order. So remember, that's another way to write that is 52 factorial divided by 52 minus 2 factorial. That's when we're considering order. That's all the possible 2-card sequences. When we care about order, if we want to divide out order, we have to divide by 2 here. Let's make this a little more complicated. How many 5-card hands can I draw from a deck? Again, when order doesn't matter. So we're going to start with order because it's easier to write out the tree, and the tree will automatically have order in it. We're going to start considering order. So this would be a permutation without replacement, 52 cards to start with. We're going to draw a hand of 5. So that's 52 times 51 times 50 times 49 times 48. That would be the answer to the permutation. If I then want to not consider order, I actually have to divide order out. It's not as simple here, though, as just dividing by 5, right? Because if you think about all the branches, there are going to be many, many branches that contain the same 5 cards, right? You could have one branch that's an ace of hearts followed by all the kings. You could have another branch that's a king of clubs followed by an ace of hearts followed by the other 3 kings. You could come up with many, many different ways to order those same 5 cards, and each of those would have been a different branch in the permutation. Now we've got to divide that order out. So what are we going to divide by here? It's not 5. What is it? Well, let's just think about it. I'm representing different cards with just colors here to make this really simple, but here's one way of ordering 5 cards. Here's another way of ordering that same 5 cards. Here's another way of ordering that same set of 5 cards. All of those for permutations, we count each of these as unique. For combinations, we want to count them all as the same. So how many repeats, how many different ways can we arrange these 5 cards? How many different orders of these 5 cards are there? Well, what does that sound like? That sounds an awful lot like a permutation. In fact, how many different ways can I arrange 5 cards in 5 spots? That's a 5 factorial. That's a permutation without replacement. So there's 120 different ways, 5 factorial. So to divide out order, we're going to have to divide here by 5 factorial. That will account for all the different ways that those 5 cards could be ordered in the original tree. We have to divide out all those different orderings. So we would take our 52 times 51 times 50 times 49 times 48 from the tree. That's our permutation when we considered order, when order mattered, and we have to divide by 5 factorial to divide out order. So now we end up with, at the end, 52 factorial divided by 52 minus 5 factorial. That's the permutation component. That's when we care about order. And then if we want to divide out order, we have to also add in the denominator 5 factorial. So what I've gotten to here now is the choosing function. So how many unique 2-card sets? We're at 52 cards. We can I want to now generalize this. So we started with how many unique 2-card sets could I get out of 52 cards? It turned out to be 52 factorial divided by 52 minus 2 factorial divided by 2 factorial. For 5-card sets, it turned out to be 52 factorial divided by 52 minus 5 factorial divided by 5 factorial. We can generalize now. Instead of putting in 2 or 5, put in r into that formula. So for r card sets, it would be 52 factorial divided by 52 minus r factorial and r factorial. And then if we generalize the 52, so we don't have to necessarily start with 52 cards. What if we start with n cards? We can get back the choosing function. So n choose r is equal to n factorial divided by n minus r factorial and divided by r factorial. That's the choosing function. So we've gone through explaining where the choosing function came from. So the choosing function, that n factorial divided by n minus r factorial, that's just a permutation without replacement. And then if we want to divide out order, we just have to add to the denominator the r factorial. So that's where the choosing function comes from. So if order doesn't matter, and without replacement, and we are only talking about when order doesn't matter, we're always doing it without replacement, we're going to use the choosing function, and choose r. So let me do some examples. So we already saw the example of the lottery. If the lottery works by picking 6 numbers from the integers 1 to 49, how many different unique combinations of 6 numbers can you choose? Well, that's a 49 choose 6 problem, so we just plug into the choosing formula. Turns out to be that there's 14 million different possible lottery answers, and only one of them will win, so your chance of winning the lottery again is only 1 out of 14 million. Here's another combination example. Now this one is actually slightly tricky, but see if you can get your mind around it. So if I said, how many ways can you get 3 heads in 5 coin tosses? You may not immediately see that as a choosing problem, as a combination. But think about it this way. If I toss 5 coins, or I toss a coin 5 times, think of each toss as being like toss 1, toss 2, toss 3, toss 4, and toss 5. I want to know how many ways can I get 3 heads from those 5 coin tosses. In other words, I want to choose 3 of those tosses to become heads, and then the other 2 will become tails, because it's a binary. So this is actually a 5 choose 3. It's a little hidden in there again, but there are 5 coin tosses, and I want to choose any 3 of them to come out heads. So that's actually a combination. It's a 5 choose 3. So that would be, it turns out to be 10. There are 10 ways to get 3 heads in 5 coin tosses. That was a little subtle, but see if you can get your head around that one. That's another way of using the combinations formula. Let's do a few more practice problems, because the only way you're going to really understand probability is just to do some practice. So we'll do some simple card hands. If you want to get into the more complicated card hands like poker probabilities, you can Google now a lot of the poker probabilities if you're curious about how to calculate those. They're similar to the logic I'm going to set up here. But let's just do it for the simple case when you're drawing 2 cards from a deck. What's the probability that you will, say, draw a pair of the same color, any pair, any 2 cards of the same color? Let's calculate those 3 probabilities. So let's start with a pair of the same color. So again, we're talking about counting methods, so we're going to calculate the total number of 2-card combinations in the denominator and the total number of pairs of the same color. And for calculating these, I'm going to ignore order. I'm going to do this with combinations. Usually it's easiest for calculating card hands actually to use combinations to ignore order. So how many 2-card combinations are there? Let's do the denominator first. 52 cards, standard deck of cards. How many different 2-card combinations are there? Well, there's 52, choose 2. So we just apply the choosing formula. 52 choose 2 turns out to be 1326. Notice that's the same answer that we solved in a different way in an earlier module. That's the denominator. Now, how many pairs of the same color are there? Well, there's no way to solve that one other than to just count them out. So there are 13 different unique faces on cards. You have everything from ace all the way up to king. There's 13 different types of cards. And how many, for each of those types of cards, how many pairs of the same color are there? Well, there's red aces and black aces, red kings and black kings. So there's 2. So it's 13 different face cards, different numbers or faces on the cards. Each of those can be either red or black, so there's 26 pairs of the same color possible. So your chance of getting a pair of the same color when you draw 2 cards is 26 out of 1326, or about a 2% chance. How about your chance of getting any old pair? Could be of the same color, but could also be of different colors. So our denominator is going to be the same here. So this is a nice thing. Now we've solved the denominator. That's 1326. Now we just have to count out how many pairs are possible. How many pairs are there in a deck of cards? So this is take a little bit of thinking about. But let's look at one type of card at a time. So let's start with aces. How many different possible pairs of aces are there? Well, there are 4 aces in the deck. We want to choose any 2 of them for our pair. So it's a 4 choose 2. There are 6 possible pairs of aces. It's a 4 choose 2. Earlier we just counted out the 6 different pairs. You can do it that way too, but now it's nice to recognize that as a 4 choose 2. 4 aces, you got to choose any 2 of them. How many different sets of 2 are there? There are 6 different sets of 2, 6 different pairs of aces. We can do the same thing for kings. It's also going to be a 4 choose 2. For queens, it's also going to be a 4 choose 2. And again, there are 13 different types of cards from aces all the way up to kings. Each of those has 6 possible pairs, so there are 78 total possible pairs. So your chance of getting any old pair is about 6%. Finally, what's your chance of getting 2 cards of the same color? So the denominator is 1326. The numerator here is just going to be, there are 26 red cards, and you have to choose any 2 of them. So that's a 26 choose 2. But then you got to do the same for black cards. So you can do 26 choose 2 for red cards, 26 choose 2 for black cards, or 26 choose 2 times 2. There are 650 two-card pairs of the same color. The denominator is 1326. So the probability of getting 2 cards of the same color is actually a 49% chance. And that might seem a little non-intuitive. You might think like, why isn't it a 50% chance? So let's look into it a little more with a probability tree so you can see why. So here's a probability tree. You can write out, enumerate all the possible outcomes here. So you have 52 cards, 26 red cards, and 26 black cards. If you get a red card on the first draw, so you're on a red branch, then you have 26 black cards left, but only 25 red cards left. Similarly, if you started with a black card, if you're on a black branch, you have 26 reds left, but only 25 blacks left. So if you count out how many different red reds there are and how many different red blacks and black reds and black blacks, for getting both a red and a red again, it's 26 times 25. For getting a black and a black, it's 26 times 25. But for getting red black or black red, it's 26 times 26. So when you count all of those out, it turns out that the probability is going to be 50 out of 102. So it's not quite 50 out of 100. So it actually comes out to be a 49% chance. Finally, I want to end this module with a classic problem from statistics called the birthday problem. And it goes something like this. In a room of 30 people, let's say you've got a room of 30 people, what's the probability that at least 2 people, that somebody shares a birthday? And I'm not talking about this sharing the same year, I'm just talking about the same date, like March 3rd. So in a room of 30 people, what's the probability that 2 people will share the same birthday? At least 2 people will share the same birthday. And what would you guess that probability is? Most people will guess something pretty small when you put this to them. Intuitively, they think, you know, the chance of 2 people in just a class of 30 coming up with the same birthday when there's 365 different possible birthdays, it seems that it's going to be a pretty low probability. Most people guess, you know, something very, very low. So think about for a minute what you would guess that probability is. And then we're going to calculate it out. So let's actually calculate together what this probability is. This one's a little tricky to calculate, so I'm just going to lead you through it. So we need a little trick, first of all, to be able to answer this one. So the first thing that we need is we need this trick. So you have to recognize that I'm asking you for the probability of at least 1 match in terms of birthdays. But I would count it as 2 people having the same birthday if 3 people had the same birthday, or if there were 2 pairs of people who had the same birthday. So I'm asking you to calculate the probability of at least 1 match on birthdays. It turns out to be very hard to calculate the probability of at least 1, because at least 1 includes many, many, many different possibilities. And so to enumerate and calculate all those different possibilities out is really, really hard. But there's a little trick we can use. We can recognize that the probability of at least 1 is the complement of the probability of none. That is, if you don't have at least 1, that means that you have none. So rather than calculating the probability of at least 1, we can always instead calculate the probability of no matches and then just do a 1 minus. If 1 minus the probability of none will give us the probability of at least 1. So let's calculate the easier thing, which is the probability of no matches, the probability of none. And it turns out to be easier. And this trick gets used in a lot of places in probability. So let's calculate what's the probability of nobody having the same birthday, of everybody having a unique birthday in a class of 30. So let's start with the denominator. How many sets of 30 birthdays are possible? Now this is going to be a case where we want to have replacement, because we want to allow that one of the possible outcomes in my class of 30 is that I could have people who have matching birthdays, right? That's the whole point of the problem. So this will certainly have replacement. Since it has replacement, and I haven't told you how to do replacement where order doesn't matter, we're going to clearly be doing in the denominator a permutation. We're going to consider order. How many different sets of 30 birthdays are there where we consider order? It's going to be 365, if this is ignoring leap years, 365 birthdays raised to the 30 power, because we're allowing that people could repeat birthdays. That's all the possible sets of 30 birthdays considering order. Now, since we considered order in the denominator, which we had to, we also have to consider order in the numerator. That's the only reason we're considering order in the numerator is because we did so in the denominator, and those have to match. So how many different ways can you distribute 365 birthdays to 30 people Now in the numerator, we want it to be without replacement, because without replacement would mean that no birthday could repeat. And remember, we're trying to calculate the probability of no matches here. So if we want to have without replacement, and we're going to consider order only because we did so in the denominator, if we want to calculate without replacement, that's a permutation without replacement. So we're going to go with our factorials. So it's going to be 365 factorial divided by 365 minus 30 factorial. That will give us all the ordered sets of where all 30 people have different birthdays, because that's going to be, so we take that and put that in our numerator, and we put our numerator over our denominator here to calculate the probability. So we calculate the probability of no matches is this permutation divided by this 365 raised to the 30. If you calculate it all out, it turns out to be a 29.4% chance. So there's only a 29% chance that nobody's birthdays will match. That means the probability of at least one match is 1 minus 29%, which is just over 70%. And for most people, that 70% is surprisingly high. They're really surprised to hear that in a class of just 30 people, there's a 70% chance that 2 people are going to share a birthday. I often talk about the birthday problem in my Stanford courses. And usually my classes might have 30, 35, 40 people in them. And so I'll actually go around and ask everybody to tell me their birthday to see if we actually have a match. And almost invariably, we almost always have a match, because the probability by the time you get 30 or more people in the class is so high that there will be a match. So it usually bears out empirically.